Hi, I'm Mike Stanzik, and this is Digital Electronics Classroom. And in this video, we're going to look at the equivalent resistance method of determining the values of a circuit or characterizing a circuit. So let's get started. The equivalent resistance method. I'm going to go ahead and draw a circuit here, and so we can take a look at an example as we go through this. So I'm going to give some values here for a source voltage of 10 volts. And we're going to call resistor 1 100 ohms. And we're going to call resistor 2 200 ohms. And resistor 3 here 300 ohms. So my first goal here, or my first step in this procedure, is to combine resistances with series and parallel rules until we get to the equivalent resistance. And at this point, we have the simplest circuit, or I like to call the simplest circuit. So when I look at this diagram, I ask myself, is there anything here that's particularly in series, or specifically in series, or specifically in parallel? Well, as I kind of go along here, I can see the battery is in series with the resistor R1 because there's no junctions in between. And then this resistor is in series with this whole section, but this whole section itself is a parallel section. And then we have the rest of it going back to the battery here, the rest of this wire. And so determining whether something is in series or something is in parallel, we have to look to see if there's any junctions in between, or for parallel, we have to look to see if they share the same two nodes. And so seeing that this R2 and R3 here are sharing the same two nodes, they have this node at the bottom that's the same, this node at the top that's the same, then we can say that these are in parallel. And we can use parallel rules to go ahead and combine them. Okay, so I like to redraw the circuit every time we make a combination. So I'm going to redraw this underneath here with the combination of R2 and R3 into one resistor. And we'll go ahead and make that resistor the color blue, because that goes along with our combination there. And I'm going to call this resistor R parallel, or R par. So how do we find the value of R par? Well, to combine two resistors in parallel, we can use the shortcut method of product over sum. And so this is going to be equal to the product R2 times R3 over the sum R2 plus R3. So doing that, we get 200 multiplied by 300 over 200 plus 300, giving us a value of 120 ohms. So our parallel here is 120 ohms. We still have R1 with a value of 100 ohms, and we still have our source of 10 volts. Those all stay the same. But now we have this parallel combination from above that is equal to 120 ohms. And notice that our circuit got simpler. So what's the next thing that I can do here? Well, I can see that now we have a series circuit between R-par and R1 because there are no junctions in between those two. So I can use series rules to combine these guys together. So this turns into a circuit that looks like this, where we have only one resistor. And that resistor, since it's the only one left, is what we call the equivalent resistance, or Req. And Req can be determined because this is series, so we can use series rules. And in series rules, the resistances add up. Req is going to be equal to R1 plus R-par, which is 100 plus 120 equals 220 ohms. So Req is 220 ohms. We also know the voltage V0 here is 10 volts. Now something interesting happens, because if I look at the nodes, we can see that Req, or the resistor, and the source, V0, share the same two nodes. So that means that these two elements are in parallel. And if they're in parallel, that means that they share the same voltage. So I can write that VEQ is equal to V0, which is 10 volts. The other thing that's kind of interesting here is that there are no junctions between the source and the resistor on either side, and so these are also in series. So when we get to the circuit that is the simplest circuit, it's both parallel and in series. And so that's pretty interesting to see that. So we know in that case that the currents will also be the same. Well, now we can use Ohm's law to figure out what the current is. And so the Ohm's law says that IEQ is going to be equal to VEQ over Req. And so that's going to be 10 divided by 220, and that gives us 0.0455 amps, or 45.5 milliamps. So now we go into our second part of the process. So the second part of the process is that we expand back out. Using series and parallel rules and Ohm's law. So our goal here is to find out the voltage, the resistance, and the current for all of the elements in the circuit. And so at this point, we have the voltage, the resistance, and the current for the equivalent resistance for the circuit, but we don't have it for the individual elements. So this is where we're going to expand back out. So we look at what the last thing we did was, and use the rules that are appropriate for that last combination that we did. So in this case, the last combination we did was the series combination between R1 and R-par to get Req. Well, what's the same in series? The current is the same in series. So since the current is the same in series, I can take this IEQ and bring it up to be the current in each of these elements above. And so this is the same as I-par and I1. So they have the same current that the equivalent resistance has. And you can kind of tell this because whatever current is going into the equivalent resistance, right, is 0.0455, is the same thing that's entering this red shape that we've drawn here. And so 0.455 is entering, and since there are no splits and no junctions, these are all in series and they have the same current. And so now we can use Ohm's law to figure out the other values here. And so I can use Ohm's law to find out what V par is. And that's going to be I par times R par, which is 0.0455 multiplied by 120. And that gives us a value of 5.45 volts. I can do the same thing for resistor 1, up here R1, and so we can find that V1 is going to be I1 times R1. That's going to be equal to 100, I'm sorry, that's the resistance, 0.0455 multiplied by 100, and so that gives us 4.55 volts for V1. Now V1 is an actual resistor, R1 is an actual resistor, so V1, I1, and R1 are the values that go through that resistor, that belong to that resistor. But R par is still just an intermediate resistor that we've made up to help analyze the circuit. So we still have to expand out from R par to our original circuit here, and that's that part in blue. And so now we're going to take a parallel combination and expand it back out to its original two resistors. And what's the same in parallel? Well, the thing that's the same in parallel is the voltage. And so we're going to take the voltage, V par, and we're going to bring it up and use it in the above circuit. Okay? So why is the voltage the same across this? Well, if you think about it, these share the same two nodes as the original R par resistor here, right? Then going back up here, these are the same two nodes right there, right beyond that box, if you will. They're right here, that node, and that node. Well, they're only this top node and this bottom node, so that means they do share the same voltage difference, and so both of their voltages will be 5.45 volts. So I can go ahead and write that in as V2, 5.45 volts, V3, 5.45 volts, and then we can solve for these original voltages using Ohm's law. So I2 is V2 over R2. So if I plug that in, we get 5.45 over 200, giving us a value of 0.0273 amps, or 27.3 milliamps. And then I can do the same thing over here with 3. I3 is V3 over R3. So that's 5.45 over 300. And that gives us a value of 0.0182 amps, or 18.2 milliamps. Now, interesting, if we add these values up for the current, 18.2 milliamps and 27.3 milliamps, you'll notice that they generate 0.0455 amps, or 45.5 milliamps. So Kirchhoff's current law is, it holds here, because we have 45.5 milliamps going through R1, and then we have 27.3 going through R2, and we also have 18.2 going through R3, so those add up to the original. So we can see that there's consistency in our solution here. So that's it. That is the equivalent resistance method and how we combine using series and parallel rules till we get to the simplest circuit, and then we expand back out until we have all the values for all the resistors that are in the original circuit. My name is Mike Stanzik, and this is Digital Electronics Classroom. I hope you found value in this video, and thanks for watching, and as always, have a wonderful day.